developed under the overall direction of the Marshall Space Flight Center by Pratt & Whitney Aircraft and Convair Astronautics. At the end of 1960, with the program just over 2 years old, the first two Centaurs are in final assembly. The first Atlas booster has been completed and is undergoing pre-delivery testing. Integrity of the hydrogen-fueled engines has been proven in repeated tests. A test vehicle has been readied for static firings at Sycamore Canyon near San Diego. Centaur's launch complex is nearly complete at Cape Canaveral, Florida, and preparations for extensive COG tests with liquid hydrogen are in their final state. I am Kraft Ericke, Director of the Centaur program at Convair Astronautics. With a few exceptions, the program is progressing on schedule, and the first flight is still planned for June 1961. However, since the last film report, there has been a change in tracking plans. Instead of using two separate tracking networks for the first 6 flights, as previously reported, we are now under direction to use this one tracking network, known as the NASANet. We expect to do 3 things with this network. First, receive telemetry data on the vehicle instrumentation. Second, receive television pictures on the behavior of liquid hydrogen during the ZOG period. And thirdly, to track the flight path. The network consists of the following stations: Cape Canaveral, Bermuda, Mid-Atlantic Ship, Gran Canary, Kano, Nigeria, Zanzibar. These 2 stations are not yet firm. Their establishment is still subject to international negotiations. A tracking ship in the Indian Ocean, Perth, Woomera, Canton Island, Hawaii, and Goldstone. These stations, with the exception of Goldstone, are prepared to receive telemetry and television data. For tracking purposes, we will be using FPS-16 tracking radar installed at Bermuda, Woomera, and Hawaii. And probably will also have the FPS-16 radars installed at Goldstone and Cape Canaveral available. One of Centaur's primary missions, as you know, is the establishment of communication satellites in 24-hour orbits. Using this type mission for illustrative purposes, we have prepared a sequence to help you visualize the vehicle's flight functions. Powered aloft by an Atlas, Centaur's first airborne moments are similar to a normal missile flight. Atlas booster engines jettison several minutes after launch, but the sustainer continues to provide thrust. The air is thinner now, causing less friction, so Centaur no longer needs insulation to protect against aerodynamic heating. After some 4 minutes of flight, Atlas completes its assignment. Separation latches open, retro rockets fire, and Centaur moves free. It is now 97 miles above the Bahama Islands, moving nearly 10,000 miles per hour. Its engines ignite for the first time, propelling it upward into a parking orbit. And now, 126 miles above Earth, it begins to coast for almost an hour. Photoelectric cells sense its attitude with respect to the sun, and they command small control rockets to point its insulated tail toward the heat source, thus reducing fuel boil-off. As the moment nears for engine restart, the small rockets return the vehicle to proper flight attitude and drive it forward slowly. The slight motion forces propellants floating free in the weightlessness of space rearward to be drawn into the engines. Centaur is north of New Guinea, crossing the equator the second time when its engines ignite again. It accelerates rapidly to nearly 23,000 miles per hour and enters an elliptical transfer orbit. Then it coasts again, this time over 5 hours, until it nears the final destination. Now its flight plane changes to the equatorial plane of Earth. Engines fire a final time, increasing the velocity, which has dropped to 3,600 miles per hour, to approximately 6,800 miles per hour. And Centaur moves into the 24-hour orbit position. Finally, the satellite separates. In 6.5 hours, Centaur has directed itself to a point 22,000 miles above the equator, approximately 1,700 miles west of Ecuador. Orbital velocity of the satellite is such that it always remains over the same point on Earth as the Earth rotates. From below, it appears stationary, locked permanently in one spot. This typical mission placed the satellite in space as a relay point for a worldwide communication network. It represents just one of the assignments proposed for the NASA Centaur space vehicle. Both Centaur stages are now in production at Convair Astronautics in San Diego, California. Manufacturing progress is reported by Senior Project Engineer Dean Davis.
By the end of December, the first 2 flight Centaurs were nearing completion, and the first Atlas booster was undergoing final testing. The Centaurs, both scheduled for completion in February 1961, are subjected to repeated testing throughout final assembly. As each of the vehicle's electronic and pressure systems is attached, it receives individual tests simulating its pre-flight and in-flight functions. Then it is operated with a related unit to determine that both perform satisfactorily as an integrated system. The majority of the testing is conducted from specially designed checkout trailers which operate the systems and record the test results for analysis. Identical trailers will check out Centaur in the hangar at Cape Canaveral. The first flight vehicle, C-1, was over 80% complete by December 31st. In late February, it will be delivered to our Sycamore Canyon test area for flight readiness firings. It is scheduled for flight in June 1961 from Cape Canaveral. Centaur C-2 was rated over 50% complete by the end of the year. In February, it will be sent directly to Cape Canaveral to be used in checking out Centaur's launch complex, Pad 36. It will then be returned to Sycamore Canyon for flight readiness firings prior to its scheduled flight in September 1961. The booster for Centaur is a modified D-Series Atlas. The first booster is designated Atlas 104D. Like Centaur, the booster's airframe is a thin-walled, pressure-stabilized tank divided into 2 propellant tanks by an intermediate bulkhead. Its propulsion system, produced by Rocketdyne Division of North American Aviation, consists of a sustainer engine, 2 booster, and 2 vernier engines. All engines burn liquid oxygen and RP-1 for propellants, and combined deliver approximately 360,000 pounds of thrust. The sustainer engine operates during the entire powered portion of flight, delivering some 57,000 pounds of thrust. This thrust structure contains the twin booster engines, which produce 300,000 pounds of thrust. It is connected to the vehicle by separation fittings and is jettisoned along with the twin engines at the conclusion of booster phase of flight. All engines, including the 2 1,000-pound thrust verniers, are gimbaled to stabilize and steer the Atlas Centaur combination. Electronic and electrical systems are mounted externally in 2 equipment pods. Unlike the standard Atlas, Centaur boosters do not have guidance systems. All guidance functions are performed by Centaur's all-inertial guidance system, located in the second stage, which directs the booster atlas by sending commands to its autopilot. The major configuration difference between the Centaur first stage and the standard atlas is in the nose. The normal atlas conical front was enlarged to a straight 10-foot diameter cylindrical section. This permits the upper stage to be the same diameter as atlas, and it strengthens the atlas to sustain the axial loads and bending moments imposed by the Centaur stage. Centaur Booster 104D was assembled and nearing completion of its final testing by the end of the year. It is scheduled to be delivered to Cape Canaveral in January 1961. At our Sycamore Canyon test site in the hills near San Diego, a special test vehicle is being readied for a static firing program. The pre-firing preparations will be reviewed by test conductor Maynard Brown.
We're directing our efforts towards proving that the hydrogen engines and supporting airborne systems perform satisfactorily as a unit. For the initial test series at Sycamore, we are using a thick-skin propulsion test vehicle. It is the same size as Centaur, but more rugged, permitting repetitive, rigorous testing. Equipped with ground test engines and related systems, the test vehicle was delivered in October to the S-4 captive test stand. This facility was constructed especially for Centaur testing. Prior to installation in the stand, the tank was covered with an 8-inch layer of stay foam insulation, which withstands repeated cold cycles. The insulation reduces the amount of heat radiating to propellants in the tank. Essentially, it duplicates the heat balance Centaur will encounter in flight. We're moving into the test series progressively, first checking out test equipment, procedures, and vehicle systems. These steps are preludes to our initial primary objective, which is the evaluation of the engines and support systems during static firings. The firings will include multiple engine starts at simulated flight altitudes. The desired altitudes will be created within the thrust chambers by supersonic diffusers, in which a near vacuum is obtained through the use of steam. By late December, we were conducting final pre-firing tests. The hydrogen peroxide being loaded here powers the pumps which deliver propellants at required NPSH to the main engine turbopumps. Cautious handling is required since, as you may know, hydrogen peroxide is extremely caustic and will ignite organic compounds or erode untreated metals upon contact. The year's final test, conducted with liquid hydrogen, was aimed at determining engine chill-down requirements and an optimum starting sequence. With the boost pump operating, a portion of the fuel was passed through the engines, which had igniters removed. Preliminary tests of this type paved the way for the static firings scheduled to begin in January. Repeated static engine tests have been conducted at Pratt & Whitney Aircraft in West Palm Beach, Florida. Status of engine development will be reported by Senior Project Engineer Richard Anschutz.
After 2 years of extensive research and development work, production of the first LR-115 flight engines is now underway. 5 ground test engines have already been delivered to the government, and an engine was undergoing a preliminary flight rating test at the end of the year. Development of the entirely new technology for this first liquid hydrogen-fueled rocket engine has required a very rigorous development program. Nearly 2,500 hours of test experience have been accumulated on engine components in this component test complex. Over 500 of these hours were devoted to perfecting the unlubricated, hydrogen-cooled bearings used in the turbopump assembly. More than 10 million gallons of liquid hydrogen have been consumed in development of the LR-115 rocket engine. To date, More than 250 engine firings have been conducted on 5 individual test stands. Newest of the engine test stands is E5. It permits simultaneous vertical firing of 2 engines under space conditions in conjunction with a Centaur propellant supply system. The propellants are stored in vacuum-jacketed tanks. The propellant supply system, which includes the tank-mounted turbo boost pumps, supplies the fuel and oxidizer to the engines installed just below the tanks. On the night of November 5th, compatibility of the Centaur propellant supply system with the LR-115 engines was demonstrated by a successful full-thrust firing on E5 stand. During a later test, a test stand procedural error caused destruction of the engines and some damage to propellant supply system components. Neither the engines nor the propellant system were involved in the cause of failure. Damage to the stand was quickly repaired, and the test program will be continued. Since the first firing in mid-1959, LR-115 engines have accumulated over 21,000 seconds of firing time during development tests. Production of the first flight engine started in November. When completed, the engines will be test-fired, completely disassembled for inspection, and then fired again. They are slated for delivery in January. Since the inception of the LR-115 program, the design philosophy has been to simplify wherever possible as a means to improve engine reliability. During the past 6 months, over 400 engineering changes have been made to improve the engine design. LR-115 engines, which weigh only 270 pounds, deliver 15,000 pounds of thrust at a specific impulse of over 400 seconds, and are capable of multiple restarts in space, have repeatedly demonstrated better than rated performance and durability. In December, an LR-115 engine began an official preliminary flight rating test. As during all engine tests, the engine is started and operated in a simulated space environment. This environment is created by discharging the engine exhaust into a water-cooled supersonic diffuser. During start, space conditions are simulated by evacuating the thrust chamber and diffuser with a steam ejector. The engine is enclosed in a tank which is partially evacuated by the diffuser to simulate space conditions throughout the operational cycle. During the preliminary flight rating test, which is being witnessed by NASA representatives, the engine must be started 20 times and must accumulate over 2,200 seconds of firing time during consecutive firings at rated duration, thrust, and mixture ratio. In previous tests, 3 other experimental engines successfully completed PFRT-type endurance programs.
Additional LR-115 engine tests are being conducted at the National Aeronautics and Space Administration's Lewis Research Laboratory in Cleveland, Ohio. I am Harry Bloomer, project engineer on the test program. Here, we will test the engine under space-like environments to determine its operating characteristics and to evaluate its overall performance. In initial tests, we will measure engine performance parameters such as propellant flow and thrust, and the rates of thrust buildup and decay during engine starts and stops. Later in the test program, engine gimbaling and operation of the propellant supply system will be investigated. All tests will be conducted in this altitude chamber. Its size permits gimbaling of the engine and operation of the propellant supply system under space conditions. A battery of 27 electrically powered centrifugal pumps evacuate the chamber and maintain it at prescribed altitudes. Engine exhaust gases are first cooled from about 6,000 degrees Fahrenheit to 125 degrees Fahrenheit before being pumped to atmospheric pressures and released in the air. Prior to engine installation in December, the chamber's propellant feed system was checked out
with liquid nitrogen during cold flow tests. During one test phase, the engine will be subjected to temperatures as low as minus 300 degrees Fahrenheit before and during firings. The severe temperatures, representing those in space, will be used for testing hydraulic systems and to define engine chill-down requirements. The LR-115 test program is scheduled to continue here until the end of 1961. The majority of Centaur's testing is underway at Convair Astronautics. Systems Group Engineer Fred Wallace gives that report.
As flight time nears, we are concentrating on design proofing and acceptance tests of components and entire systems. One test series conducted at Point Loma confirmed the design worthiness of the umbilical booms, which will service the Centaur vehicle at the launch pad. The top boom supports electrical cables and an air conditioning line for Centaur's payload, plus a line to carry vented hydrogen gas away from the vehicle. Propellant and pneumatic lines, electrical and instrumentation cables are on the lower boom. Liquid nitrogen was used in the propellant lines to simulate the stiffness which the fuel and oxidizer will cause during propellant loading. Released by an electro-hydraulic system, the connections break free at intervals ranging from minus 30 seconds to the moment of 2-inch vehicle motion, and the booms swing back to vertical within 3.5 seconds after the final disconnect. This boom system was shipped in December to Cape Canaveral, where it will be mounted atop a 70-foot-high service tower at Pad 36. The thick-wall Centaur cruiser tank continues as the testing mainstay for fuel transfer studies and evaluation of the propellant utilization and boost pump systems. By the end of 1960, some 300,000 gallons of liquid hydrogen and 62,000 gallons of liquid oxygen had been used in this tank and its predecessor without one serious incident. One test series confirmed that the insulation panels, which shield propellants from aerodynamic heating during early flight, can be jettisoned from a cold tank. Initial attempts had failed because of insufficient spring force behind the test panel. Additional springs were added until the panels now jettison properly. Another design proofing trial for the insulation panels was conducted in a wind tunnel at NASA's Langley Field, Virginia Research Center. In tests of the panel's structural integrity, the primary objective was to determine if it would flutter while subjected to flight-like aerodynamic and thermodynamic conditions. The test panel was half the length of a flight article because of space limitations in the chamber, but it was full-scale in radius and thickness. During the test, liquid nitrogen was circulated through the fixture on which the panel was mounted to simulate Centaur's hydrogen-chilled tank walls. Helium gas purged between the panel and the mount prevented freezing. A 1-ton steel shield, designed specifically for this program, protected the panel from shock waves at the beginning and end of the test runs. Operated hydraulically, it exposed the panel after the tunnel started and covered the panel before the test terminated. Compressed air ran through the tunnel at a velocity of Mach 3 for all tests in the series. Pressures on the panel were varied from 1,500 pounds per square foot to 5,000 pounds, and temperatures ranged from 300 to 600 degrees Fahrenheit. The strength and stability characteristics of Centaur's insulation panels were confirmed under environments exceeding in severity those expected in flight. Another crucial test series verified the design worthiness of the centrifugal vent valve separator, which will relieve pressure in Centaur's fuel tank. It works on the principle of a cream separator, with spinning vanes allowing gas to escape while forcing the heavier liquid back into the tank. On the vehicle, the separator will use energy from the escaping gas for self-power, but for the test, it was driven by a small motor. Liquid hydrogen was shaken violently to simulate the fuel's frothy, unsettled state, which the separator will encounter during zero-gravity conditions. In the field of electronics, one program is evaluating autopilot components operating in conjunction with Centaur's engine gimbaling system. On this autopilot test stand, the servo amplifier unit, which directs engine gimbaling, has undergone 135 hours of tests to calibrate frequency responses and to validate design worthiness. Signals to the servo amplifier, normally supplied by a rate gyro unit, are generated in the control console for test purposes. Simulated engines duplicating the mass of the flight engines and related control equipment are mounted on a water-filled tank consisting of Centaur's forward and aft bulkheads. Tests to date have revealed no design problems with the servo amplifier, but they did disclose that both engines were twisting during gimbaling. The malfunction has been corrected by redesigning and strengthening the gimbal and gimbal mount, and by relocating actuator attach points. By the end of the year, the 3 telemetry units for Centaur had completed design proofing tests, including 500-hour endurance requirements and evaluation under environmental extremes. 2 additional units for fuel behavior studies are now in development. The first Centaur guidance system completed its acceptance testing program in November and is now installed aboard the initial flight vehicle. Evaluation tests are currently underway to appraise design improvements in follow-on systems. Another test program underway is the investigation of zero gravity, the environment in which Centaur will operate. Reviewing that program is thermodynamics engineer Joan Shirley.
Since zero gravity is a relatively unexplored environment, we have been concentrating much of our efforts on developing the methods and equipment to investigate it. Many experiments are conducted with this drop test apparatus, which can provide nearly 1 second of zero G, or weightlessness, per test. Part of the unit is an instrumented package containing a dewar for liquids and a high-speed camera to record their behavior. When snapped upward or dropped, the package simulates a free-falling object, and the fluid inside reacts as it will in space. Liquid hydrogen is being used here. In addition to studying fluid behavior, this experiment is aimed at selecting a sensor capable of distinguishing between liquid and vapor. These tests also support forthcoming aircraft heat transfer studies. More data must be obtained from this and other experiments before positive conclusions can be made on the effects of zero gravity. Airborne experiments conducted in a KC-135 during the past 6 months have been concerned primarily with perfecting test techniques and equipment. The objectives of the airborne program, like the ground tests, are investigations of liquid behavior phenomena, heat transfer studies, and evaluation of certain Centaur components. During the jet missions to date, we evaluated several test devices using water or liquid nitrogen, but more importantly, we worked out the procedures to provide maximum pre-floating time for the test capsule. By late December, we were making final preparations for a series of airborne experiments which will be conducted within a nitrogen-filled collapsible test cell. The cell undergoing checkouts here will be used for liquid hydrogen studies. During flight, a gaseous nitrogen environment will be controlled inside the cell, thus preventing mixtures of hydrogen and oxygen from reaching combustible proportions. The cell and related equipment were loaded aboard the KC-135 at San Diego on December 21st and flown to Wright-Patterson Air Force Base, Dayton, Ohio, for installation in the plane. Current schedules call for initial flights with the test cell in February 1961. Another phase of the zero-gravity investigation is now in the preliminary stages at Holomore Electronics in Anaheim, California. The company is developing a television instrumentation system to monitor liquid hydrogen behavior in Centaur during flight, and particularly during zero-G conditions. By the end of the year, a working breadboard of the system's camera was in test. It employs slow scan television techniques, allowing narrow bandwidth, low power transmission of the pictures over extremely long distances. Scheduled to be flown in the first 3 Centaurs, the system will transmit visual data to ground monitoring stations for recording on magnetic tape recorders. The data can then be viewed on TV monitors or transferred to film.
With only a few months remaining now until the first flight, the tempo of the entire program will increase considerably. Milestones immediately ahead include static firings with the propulsion test vehicle and the flight readiness firing of the first Centaur. Another highlight will be the erection on Pad 36 of an Atlas Centaur vehicle to check out that facility. By December 31st, the blockhouse and the launch and service building were finished. The service tower and the propellant loading system still remain to be completed. Plant erection dates remain firm, with the Atlas booster scheduled to go into the stand in early February for checkout. Because of the increased activity in the program, this Centaur film report will now be produced every 3 months, beginning January 1961.